Hi everybody, welcome to another video in Calculus 3. We go to chapter 14, vector value function. So we'll study about vector value function. So a vector value function is the vector and it's also a function because it's the function of maybe more than one parameters. We'll talk about that in a minute. But first, specifically we have curves in space. Curves is one-dimensional object and space is three-dimensional space. It could be in this space we refer to three-dimensional space, right? So it is a function and it is the vector, so it has three components. A vector in space, so it has three dimensions, three components, right? And this is one-dimensional object because we have one parameter t, and says every parametric equation we have to have the range or the limit or the domain for t, and if it is a vector value function, the domain is the largest set in which each component function those are component function are defined. So all of them have to be defined for a parameter t. So that's what we define. That's how we define a curve in space. It's a vector value function, right? So curve in space. Right. Let's look at first example. Find a vector function or the vector value function for the line passes through the point 2, -1, and 4, and 3, 0, 6. So we have 2 points P and Q. And we just find a line go through those 2 points. So that's simple enough, right? We did this previously, and we said equation of a line go through 2 points is equal to we have the initial point, 1 point on the graph, plus TV, right? Now, what we have here, instead we have 2 points, so we can say R equal to, let's choose the point P, and then plus t times the vector PQ. And then for both of them, we need to have t between -infinity to infinity. Yeah, for both of them. Right. So we need a point and a direction vector for a line. Right. So simple enough. The vector PQ, of course, is P Q minus P. So first vector PQ is equal to Q minus P. Q is 306 minus 2, -1 and 4. 3 minus 2 is 1. 0 minus -1 is also 1. 6 minus 4 is 2. So that is vector PQ. And finally, the line PQ we write R equal to P plus T times vector PQ. So we can write as point P. Either we write a point or as a vector, doesn't matter. And then T 1, 1, and 2. And then when we combine them, we will have 3 plus T, 0 plus T, and 6 plus 2T. Right, so pretty much that. And of course we still need to have T between -infinity to infinity. So like I said, nothing new here for equation one line. Or we can say this is f of t, g of t, and h of t. Right, so no big deal. And all here we can write that as x, y, and z. Or we can just say r is also a function of t. So there are a lot of different ways to write this, but bottom line is it is a parametric form or parametric equations. So we have three functions of t. Parametric functions, three functions of t. Right. Next we have this. Find the vector function for the portion of the problem y equal to x squared from 0 to 2 and 4. But the parameter is between 0 and 1 instead of what we can choose. Right. So if we have y equal to x squared, naturally we will let x equal to t, then y equal to x squared will equal to t squared. So that's a good choice. If we have a function like this, just let x be t, so y equal to x squared equal to t squared. Right. So the parametric form or the vector value function we can write either like this, or we can write like x and y, where x is equal to t and y equal to t squared. Right. That's good and all, but notice that in this equation we do have x go from 0 to 4, sorry, 0 to 2. So if we write like this, t is between 0 and 2, right? Those values. That's not what we want. What we want is the parameter between 0 and 1. So how do we do that? So to do that, we just need to convert this into 0 and 1. So I will just divide everything by 2. So in that case, I will have 0 t over 2. Right. Now, if I replace this by s, for example, so now if you replace this by s, then we have s is between 0 and 1, right? So I will make a substitution in here because I see this is equal to something, so let that equal to s. So let s be equal to t over 2, multiply t over, we have 2s is equal to t, right? So we're trying to get from 0 to 1, and we'll convert that into s. Right? Now, 2s is equal to t, so I will substitute in here. So we have x and y. T is equal to 2s, right? And t squared 2s squared. So that gives us 2s and 4s squared. And we still have two components, x and y. And finally, if we want it to be t, and then just write that in terms of t, we want to. Now replace the s by t. We just say we have 2t, 4t squared, and then t replace to s, we have 0 to 1. Right. So yeah, so a few things we can take out, we can get from this problem is that when we have y is a function of x, or x is a function of y, just choose one of them to be t, and the other one we follow. And if we want to change into some certain domain, we change that to a certain domain first, and then solve, let s equal to that, and then solve for t, and substitute back in for s. And at the end, if we want to, we can always rewrite the s as t. In that case, we have this. Right, how do we know if it's correct? A calculator can graph a parametric equation, but only for two variables, only in the plane. So in the calculator, I will choose function and I go to parametric. And now let's graph 2t, 2 times t for x, sorry. 2t and then 4t squared. And we can hit Windows. We go from 0 to 1. And the increment, let's graph 100 point. So from 0 to 1, the width, the length is 1. And we'll divide by 100. So we will graph 100 of a point, 100 of a unit. And then we hit graph, and we see we have a parabola from 0, 0 to 2 and 4. Right, so that's correct. Right. Now, one more thing to get out from this is y equal to x squared. If we just hit y equal to x squared, it is a parabola, right? Normally, it doesn't have any limits. It goes extend on both sides. It doesn't have any direction. But when we write like this, there is a direction, as you see. In this case, it did say from this point to that point and not the other way around. So we do have a direction here. And so that led to a definition of what we have next. All right, parameterized. By the way, this is one way to write this. The word parameterized curve, meaning that we write the curve in the parametric form. You might see this spelling also, parametrized, instead of parameterized or parametrized. Those two, both of them are acceptable. Haven't said that. I think this one probably a little more precise, because usually we say parametric curve, for example. So that form and that form is more consistent than parameterized. But you see that in different textbooks. Somebody use this and somebody use that, meaning the same thing. Right, enough for the English lesson. What we mean when we say parameterized curve is that we write a curve in parametric form. So we write that in the vector form where we have this. And the problem with that is when we write t from A to B, it has a natural direction to it from A to B, right? And we define a positive or the forward direction in which the curve is generated as the parameter increases from A to B. So that is the natural direction when we write a curve in the parametric form. Right. Or another way to define that is the positive direction is in which the tangent vectors point in the same point along the curve. So if we have a curve here that has no direction, the vector, tangent vector can point either way. But if we have the parameterized curve, the curve going this way, the tangent will be pointing in the same direction as that. And this is parameterized curve, and it has the positive orientation like that. Right. Now let's look at some examples. Sketch the curve described by this equation. Right. So I have that, and forgot about that first for a moment. Look at the two dimension R and J in the XY plane. Let's just graph it and see what happened. 4 cosine of t and sine of 2t. Right, 0 to 2 pi, 0 to 2 pi. All right, let's graph 100 point from 0 to 2 pi. I divide by 100. All right, let's see. Oops, what's wrong? All right, let's keep this in the radian mode. Oh, maybe because of this. Right. Wait. That's interesting though, but that's not what we looking at. There's no T here. Sorry. I look nice. So. Anyway, so this is an ellipse. Right? Let's see that again. Yeah, it is an ellipse. And it goes from that to that. All right, let's just say if we don't know that. Now just let this be x. And this is y. So we have 4 cosine of t equal to x. Let's solve for cosine of t. Cosine of t is equal to x over 4. And then let sine of t be y. And so we still have sine of t is y. Now let's square both sides. We have cosine square that, and then sine square. So usually when we have both sine and cosine, we do use this trick to eliminate the parameters. Cosine square plus sine square is 1. Four square, just 1 square. What we have here is, yeah, cosine square plus sine square is 1. What we have here is an ellipse. Now, not only that, we know the ellipse, the 4 below the x, so will be 4 units on the x, and negative 4, 1 up, 1 down. So we have an ellipse. And from 0 to 2t, when t equal to 0, we have 4 and 0. So actually we start here and then we go in that direction. If that is only x and y. However, we have t here. We have z equal to t over 2 pi. So equal to t over 2 pi, meaning that the bigger values of t, the bigger values of z. So as t increases, z increases. So t increases as z increases. So one increase, the other one increase. So imagine we have just an ellipse on the xy plane, and then the z increase, so we just have higher and higher. So essentially what we have is like a spring or a helix. Anyway, so try to draw with pencil here. So on the xy plane we will have an ellipse. Right. This is x, y, and z. Right. Now, we start at the point on the x-axis. We start 4, right, and go this direction. However, as we go along, the z increase in values. When t equal to 0, z equal to 0, and when t equal to 2 pi, z equal to 1. So z will go from 0 to 1. And let's say there's above that. There's another. Right. The curve will go from here. Yeah. So it increases in the height. And just what we have is a spring. Yeah. So think about this. We probably have an ellipse like this. I'm going that direction, but then we have the height increases, so it will be like that. And when we have t increases from negative infinity to infinity, what we have is we still have an ellipse. But t could go from negative infinity to infinity, so z will go to infinity to negative infinity to infinity as well. So we will have when t between negative infinity to infinity, we start from this point, and we just go with the spiral. I'll just go like that, because in the other direction as well. So just have a spiral like that. When t go to negative infinity to infinity, so z will go from negative infinity to infinity as well. So we just have that. This will only go one revolution from 0 to 1. So the direction is that direction. So yeah. So that direction. Just keep spiraling like that. Right. So next, we graph this curve, which also once again, if we have sine cosine only, that is an ellipse. Moreover, this is a circle, right? So let's just say x, y, and z, right? So x, we let cosine equal to x and sine equal to y. Since we have cosine and sine, let's square both sides, because cosine plus sine square is equal to 1. So this is a typical technique. So once again, we have a circle. So if we look from the top, it's going to be a circle. However, the z will changes. From 0 to 2 pi, what we see here is the 2t. So let's say z equal to 0.4 sine of 2t. If we just graph that function, now we just graph the function, not parametric form anymore. Let's just graph function. How about 0.4? 0.4 sine of 2t, or 2x if you will. Right, so it's like that. So from 0 to 2 pi, I need to zoom out. 0 to 2 pi, it go from here and right. Anyway, as this graph. But what I'm trying to say here is there's a 2 here, meaning that the period is equal to pi. So if we're going to graph that function of t, z, sine will go from 0, so we have 0, so it will be like that. Yeah, because I graphed too many points probably, but anyway, so meaning that 0 point sine up to t, when t equal to 0 we have 0, so we start from here and we go up and down and then back to 0 and then up and down and then back to 0. So which means that in this graph of that 0.4 sine of 2t, we have 2 maximum, 2 minimum, and 4 points equal to 0. 1, 2, 3, 4, and 5. So 1, 2, 3, 4, and then back to 5. So in that case, what we have is kind of a roller coaster, right? Or if you think about this, this is more like a potato chip, let's say Pringles. Look like that, right? On the top, it look like a circle, but on the side, it look like that. Not quite a potato chip, but we're talking about the boundary of it, so kind of like that, right? Yeah. So if we, let's say 4t instead of 2t, it will go up and down, so there will be 4 maximum and 4 minimum. In that case, it will look different. Yeah. In this case, because of the 2, the period is 2t, 2 pi divided by 2, which is pi. So the graph like this, there are 2 maximum, 2 minimum, and 4 zeros, and then get back to it will be 5. Right. So that's what we have. Right. Limit vector value function. So we define the limit, like, of course we can use the epsilon delta like we used before, but just proper notation. We say the limit of the vector values function is just limit of the vector value function is the vector values function of the limits, right? That makes sense. So limit of the vector values function is the vector value function of the limits. So if all of them have limits, then the limits of the vector value function equal to the limits, the vector value function of the limits. Right, let me say that again. A limit of a vector value function is the vector of the limits, because here are constant, so we don't have a function here anymore. Bottom line is, we just find the limit of each one of them. Simple enough, right? Yeah, that's all there is to it. Usually we can write I, J, K, but sometimes when I type in like this, is a lot quicker than using I, J, K with the boldface at I, J, and K. So I use the bracket notation in place of that. And besides, this usually takes less space than that. Right. But once again, if we want to find a limit, just find the limit of each one of them. All right. Evaluate the limit of this function as t equal to 2. So simple enough. So limit is t equal to 2 of the vector value function cosine pi of t, sine of pi t, e to negative t. Right. Limits. limit of vector value function is the vector of the limit. If it exists though, if those limits exist. So we put the limit on each one, on each component function. That's easy, right? Just put 2 in for t. We just have cosine of 2 pi. Sine of 2 pi. E negative 2. Right, cosine of 2 pi is 1, sine of 2 pi is 0, and e to negative 2 is e to negative 2. I don't know what that is, but right, so that's what it is. E to negative 2, what's that? Oh, the calculator is still frozen. I just reset it. Right. Yeah, I don't know what happened. Right. We need e to negative 2. Right, about that 0.1. So I guess when t approaching to 2, we have a point, let's say 1 on the x-axis. So it's about there. It's about right. Let's say that point. Right. Now evaluate this limit as t go to infinity. Now this is interesting. So first we put the limit to the cosine pi t, sine of pi t, and e to negative t. First of all, limit of t go to infinity. Remember the cosine function or the sine function, the graph is the wave, right? If it is the wave, when it go to infinity, it does not approach to any number. So that one we say this limit does not exist. This limit does not exist because sine and cosine do not approach to any number as the variable goes to infinity. However, e to negative t, let's graph that function. We have e to negative x. Let's just graph that. Right. So it's like that. So as t go to infinity, if we see if this function continue, it will go to 0. So I usually prefer to use e to the x instead. Exponential function looks like that. On the negative infinity side, it go to 0. So limit as x goes to negative infinity of e to the x is equal to 0. On this side, it go to infinity. So this goes to 0. So in general, we say the limit does not exist because one of them does not exist. We only need one of them does not exist. The whole thing does not exist. However, in this particular case, remember, if we have sine, cosine, it will just did like what we did earlier. That equivalent to x squared plus y squared equal to 1, right? So if we consider this two, equivalent to x squared plus y squared equal to 1 if we only have x and y. Now, so that's still regardless of t increases, it will just go in the circle. When they have the z component, then we have different altitude, different height. But if we don't have the height, if the height is 0, we just stay on the circle. So that's why we said the curve approaches the circle x squared plus y squared equal to 1 as the xy in the xy plane as t go to infinity. However, if we ask for what is the limit of this function, we still say does not exist because one of them does not exist. But even though it does not exist, we know that will be on the unit circle on the xy plane. Right? So, the limit does not exist. We don't have any particular point for the limit, but we know those points on the unit circle on the xy plane. Right. Now sketch this one. T cosine t and t sine t. Let's graph the parametric equation and see what happened. Parametric. Gradient mode is right. Let's graph t cosine t, t cosine t. When we set the calculator in parametric mode, you see function parametric polar sequence. And now look at this x, t, theta, and n. For a particular mode, when we hit that key, it will give us the corresponding variable. So since we're in the parametric mode, it is using t. Let's go a little further than that, about 4 pi. So what we see here is a spiral, right? So it is a spiral on the xy plane. So how do we write that? How do we know if it is a spiral? Right. Let's look at this equation. Once again, we let x equal to the first component and y equal to the second component. Try to eliminate the parameter. Right. X equal to t cosine t. Y equal to t sine t. So cosine of t is x over t. Usually I will solve for sine, cosine, and then square both sides. Let's square both sides. Cosine square equal to x square will be x square over t square. So square y square over t square. Now let's just add cosine square plus sine square is 1. We have x square over t square plus y square over t square. So that's good. How about we multiply both sides by t? Multiply this by t square. We have t square equal x square plus y square. That's good, right? Now, but remember in polar coordinates, x equal to r cosine theta, y equal to r sine theta. X square plus y square is r square. And tangent of theta is y over x. So that's what we have about polar coordinates. So x square plus y square here is equal to r square. So we have r square equal to t square. Take square root on both sides, and t is only positive. So we can say r is equal to t. Meaning that as the angle increases, the radius will just increasing. So whatever the angle is, the radius will get bigger and bigger. So essentially we have a spiral like this. So that is in the xy plane. So if we look from the top, that's what we see. Now if we look from the side, what do we see? Let's look at z equal to ln of t. Now we'll go back to function mode and look at ln of t, ln of x. Now okay, that's good. Right, so it's like that. Okay, so let's see. Okay. No. So z equal to ln of t look like this. Ln of t, as t go to 0, it will go to negative infinity. So this go to negative infinity, and this side go to infinity. So what we have is a spiral with the z values. Increase like that. So what does that look like? So when we have the spiral, the bigger the t, the further away from the z-axis, right? Because z is equal to ln of t. This is also increasing. So if we have 0, then we have the bottom. Actually, we worry about that when we have the limit of 0 later. But when we put all of this together, what we actually have is the spiral. We just get the altitude just increasing and increasing, and it looks like a tornado. When z go to 0, when t go to 0, this go to negative infinity. So essentially, it's just like tornado, and this is the limit when t go to 0. So we have a tornado when t go to infinity, just get further away from the center and higher up. But when t go to 0, so limit of ln of t as t go to 0 plus is equal to negative infinity. But when t go to 0, that go to 0, that go to 0. So we say that the limit of r of t when t go to 0, this go to 0, this go to 0, as t go to 0 is equal to 0, 0. And I know it's not technically like that, but we still say it does not exist because we have infinity there. But we know that we'll approach into the point down here. So it's kind of a tornado. It's still swirling around, but very close to the axis. As you see, the spirals are equal to t. When t gets very close to 0, it's very close to this axis. But when t gets close to 0, it goes down to negative infinity. So when here it go to that point at t go to 0 from the right hand side. But we still say it does not exist because infinity is not really a number. So anyway, I thought that is an interesting example. But that's all we have for this section. See you in another video in Calculus 3. By the way, in the next section, we actually it's going to do some calculus. Up to this point, we haven't done any calculus yet. But we start that in the next section. As always, thank you for watching.